Okay, time for a little show and tell. So, I've been uh, prototyping these ball and cup assemblies, which are one part of David Hamel's uh, devices, which were nonlinear Magneto-Mechanical oscillators. And I'm attempting to just sort of get a feel for this part of the assembly. So basically, it consists of two cups and one ball, and the diameter of the cups is twice that of the ball, so that when these are together in the center, if you were to look at a cross section on the side, it would form a vesica Pisces. But for practicality's sake, there's a gap because there needs to be a gap, otherwise these edges would run into each other. Now, without the top magnet, I'm just going to show. Basically, this has, if you assume that this top piece doesn't tilt, right? Let's say, for example, the way that David Hamel did this was he had three of these assemblies and a plate on the top and bottom that connected them together. And from that geometry, you could assume that that these would stay, the plane of this and of this would stay parallel. So assuming that those stay parallel and moving it like so, you can see that it has a centering stable equilibrium. When you raise it out of the center, or when you pull it out of the center, it raises. So that gives some natural centering action to it. Now, when we add these really gnarly ring magnets in opposition, what I find is that getting it right about there. Okay, so I'm holding the support ring, but not the magnet itself right now. So it's floating there, if you can see that. And that's if I bring just the support piece with the cup up, it's just a little bit before it starts floating on its own. So I know that that's the repulsion point for the strength and the weight of these magnets. It's actually pretty far. That's like 3 inches, almost 3 inches that they're repelling. Okay, so holding the top magnet and moving it along here, definitely get right away. I get the sensation right towards the center there that I guess you can't really see this, but it wants to spin the ball. It's like there's one little orbit there, small, not zero, where the ball just wants to go. And it's hard to show that here, but I'll think about some better ways to do that. Anyway, I just printed these two parts today and the other parts a few days ago, and it's been a series of printing these things just to get them so that they can, like, this is a screw mechanism, and so is this one, but it's shallower. So I was experimenting with the distances, or the heights rather. As you can see, these are 3 different heights, and I actually have 3 of these spheres also. But I'm just prototyping the one for now until I get them right, and then I'll print 3 sets. And one other detail I should mention is that the bottom of David Hamel's device had 3 of these ball and cup assemblies, but only 1 set of ring magnets, and the ring magnets were centered between the 3 ball and cup assemblies. But I have the possibility here of having these magnets on all 3 of the ball and cup assemblies. And that's actually kind of an important point that I should mention conceptually as far as what we're really looking at here. So the ball and cups are a stable equilibrium, but the magnets in opposition, here, let me show you like this. So I'm going to attempt to keep the top magnet equidistant with respect to the amount of force, repulsion force I'm feeling. And you can pretty quickly see that there's an arc there, right? An upward shaped arc. Well, with the ball and cup assemblies, it's a downward shaped arc. So what we're doing here when we put these together is we're mechanically superposing an unstable equilibrium and a stable equilibrium. And it's kind of uncanny. It's hard to describe how it feels, but there's this one little part there where it just feels like it wants to sit in a pocket. And it won't. This will tumble over. But yeah, some interesting progress so far. And yeah, thanks for coming to my Ghetto TED Talk. More to come soon.